Hi and welcome back to Podcast School. This is a technology and design podcast for AS level, and we're looking at SIA Unit 1.18 of the new revised syllabus. So today we're going to be looking at combining components as input devices and in particular timing circuits. Okay, so I've said there that there are many electronic applications when we need to generate a time delay. Sometimes we need to provide a regular on-off pulse, and sometimes we need to switch an output on or off for a period of time. So those are the two types, so either a pulse or constantly on or off for a period of time before returning to its original state. To enable us to do either of these, we need to build a timing circuit. Okay, so this section is all about timing in electronics and how we might go about, making circuits figure out what time has gone past or gone by. I've also said there that the delay and timing circuits are common in electronic systems. Electronic clocks, televisions, video recorders, many things all require timers for them to operate. Okay, so that's sensible. I've shown you here a diagram, and you can see that there's some zeros along here and some ones, so it's a bit pattern. The middle, or this second one up, is actually a stream of ones and zeros, and you can see it's uniform. That would tell you that that is a clock pulse, and we'll talk more about that later. Now, the first type of timing circuit we're going to have a look at is something called monostable, and a monostable timer has one stable state and one unstable state. Now that becomes clearer when we look at the diagram. Okay, so for a time t, there will be an unstable state. That's a time whereby the output of the timer is at a different position to what it normally would be. Alright, so normally this timer's output is low, that's the stable state, but for this unstable period of time t, it goes high. Alright, and it will do that after it being triggered in some way. So it's created it's created a single pulse or signal. So that's a monostable timer. Another type you might see is an astable timer. It has no stable state, in fact. It just switches from one to the other, from low down here through to high, and it will have two periods of time associated with it. It'll have a time whereby it spends being high up here, and also a time when it spends being low. Neither of which are what we would say are stable. They are both a timed period of time, and they will change. That is astable. Okay, so let's have a look at what I mean by RC timing circuits. In fact, I haven't said it here explicitly, but R means R stands for resistance and C stands for capacitance. And we use resistance and capacitance to create time delays. If you were to look here, the resistor and the capacitor are in series, and if we put in a voltage supply Vn, what you'll find is that the capacitor will begin to charge, but not in the same way that you might find a bucket, for instance, would fill up if it were connected or if you put a hose into it. It would fill up linearly until it was overflowing. The capacitor doesn't do that. You can see its charging characteristic here by this blue line. It charges quite linearly at the start, and by linearly I mean in a straight line, and then somewhere around or just after 63%, it starts to tail off, or it starts to gradually slow down until it basically flattens out. Okay, so you should recognize that shape of graph as a charging graph. So how might we charge this capacitor? Well, here's a circuit that will do the job, okay? You can see that there's a switch in here, S1, and there's also another S2, and it's connected to a voltage supply here, in this case it's 9 volts. And you've got it, whenever S1 closes, the capacitor C1 begins to charge through R1. And if we were to plot the charging graph, you would see that it charged just as before in a linearly at the start and then tailing off. Now, there's a few things that we need to make sure we've understood here. The charge rate depends upon the product, i.e. the multiplication of the capacitor value by R, the resistance value. And in fact, that's called the time constant. And you'll find out that the time constant is the time taken for the capacitor to reach 63%, roughly about 2/3 the supply voltage. I've said there, if T is large because C and or R1 is also large, then charging occurs slowly. The capacitor will charge to 2/3 or 63% roughly of the supply voltage in one time constant. It will then charge to 2/3 of what is left, and so on. In practice, the capacitor is fully charged after 5 time constants. Okay, and here we go. Here's another graph. You see the charging graph as before, but also the discharging graph has a similar shape, but obviously in the mirror and rotated view of that. Okay, so it's in this case it charges fast and then starts to slow down, and in the discharge it discharges slowly and then starts to slow down. But if you'll notice, after about there's 5 time constants, we can say that the capacitor is fully charged. Oh, and look, in this circuit you can discharge the capacitor again by releasing S1, so disconnecting it from the voltage supply, and also by pressing S2, which will allow it to discharge through R1 this time. Okay, so I've already mentioned a lot about this, about the discharging, so I'll not spend too much time on this. And remember, 5 time constants, we can say that the capacitor is fully discharged. Now, an important note here, and I'll just read this out word for word. I've said, remember, the voltage will rise or fall to approximately 2/3 or 63%. Now, you might be thinking, well, 2/3 isn't 63%, but it's actually the value is the time constant is 63%. I've just said approximately 2/3. It helps us remember. It's really 63% of its final voltage in one time constant. Now, here's the important bit. It will then rise or fall to 63% of the remainder in the next time constant, and so on. So it charges to 63% after one time constant, and then 63% of what is left to charge in the next time constant. The capacitor is considered to be fully charged or discharged in 5 time constants, and we've already seen that. Okay, and I've already alluded to it. The time constant can be given by multiplying the value for R, which it's charging through, times the capacitance itself. And you should remember that T is in seconds, R is in kiloohms, 1000 ohms, and C is in microfarads. Okay, here's a circuit that we can use to actually create a time delay. Alright, you can see here that the capacitor has got a switch with it here. And what happens is the 9-volt battery is connected through the variable resistor, and when in this position, in this double throw switch, it can be charged through the poles and through into the capacitor when it's in this position. But while it's in the other position, of course, then the capacitor will discharge. In fact, it's not a great circuit, this, because what will happen is the capacitor will be short-circuited. So not really a good example here of a discharging circuit. But what it will do is it will charge just in the same way that we've seen before. Okay, and the time taken for it to charge, the time constant, will be determined by C, the value of C, whatever the R1 is set at that period of time, times R. Sorry, C times R, yeah. Now, I've just shown you this large again, just for clarity. Now, remember how a transistor works. Once the value of the voltage at the base is above 0.6 volts, then the transistor will switch on and allow the buzzer to buzz. So I would imagine that the capacitor will charge to, well, more than 0.6 volts very, very quickly there. In fact, you could work that out. Okay, so that's it for today. I've left you just with some references where I've taken some of this information from. I'll also put these references on the website as well, so rather than actually having to write these down, you can click directly on them. If you have any questions, don't forget you can email me at info@podcastschool. Remember to pick up the PDF notes that accompany this video podcast, and don't forget to subscribe as well, so you don't have to keep, if you're actually coming to the site and watching online, you can actually download the video podcasts automatically simply by just subscribing through your iTunes. Okay, so that's it for now, and I'll see you next time.